I'd like to set up for our project, give a little background of some of the research I did, some of the thinking behind why I'm asking you to do this project, hopefully for you to get more out of it. And so let's just start with the idea that, well, let me just go ahead of couple here. This is actually the project we're going to do, but we're really not making the building. We're really looking at the superstructure roof system. It has louvers on it. I think in the project, I'd rather us conceive those to be like solar collectors. But we have these long, slender columns and this kind of structural grid. And the whole crux here is to really lay out this grid system, to do some basic calculations about the strength that needs to be in this column system to support a load system, and kind of the thicknesses of those beam elements. So let me just jump back here right away, start with the conversation about kind of the review of this idea of tributary area. So we need to be able to, and you should be able to understand this idea of contributing, the loads that get contributed to any specific element. Comes from kind of half the span width in each direction to the next element. So this column system that we're indicating here, you can see it's going halfway to the next column assembly, and it's a little difficult to see here because this is kind of a rotated 3D view, and it's halfway to the other column system that would be supporting it in the center here also, and it's the same on the other axis, so to speak. So keep in mind that idea of tributary area, this idea of special conditions. The end beams now, because of that concept of tributary area, the end beams do not need to be as large because they're only carrying half of the weight that the interior beams would carry. And then we'd be able to need to start kind of making estimates about the kind of loads. And I would bring you to this site. This is hyperlinked, so it'll take you out to this ATC hazards by location, and it'll give you the wind loads, the snow loads, and the seismic concerns of any specific site. It turns out that it's really difficult in our area to get that information. You can see if we did Chicago, we would have no problems gaining this data for things like snow loads. But in our region, they're actually, that highlighted red area means that it needs to be a specific case study data, and that might be just available in the local building codes or other parts of the International Building Code Ordinance. But this is a good research or resource. And then we have, once again, I'm pointing you out to these ideas of these load and column tables that we get. They have all kinds of very rich information. Some can give us very direct information about how much the carrying capacity is of the element that we're using. In the case of our project, we will be using a custom shape, and we have a calculator that we're going to be able to take into use. I don't know if this is new information or not. I don't know if this was contained in your structures course. It's really kind of a critical understanding for architects. So I'll just take a minute to kind of go through this. This idea of how much load a column can support depends on the connection systems that it is attached to on both ends. So for instance, a stiffer column with a theoretical K value that's less, should I say, and that works out in the calculation to be stronger, is pinned on, or is fixed rigidly on both ends. That means that in the case of this column here, you're seeing that very small buckling region, as opposed to one over here, which has a very large buckling region. And that's because this is actually this rigid connection up at the top and bottom are working to help stabilize or reduce that buckling. So this column, by the nature of the way the ends are fixed, is stronger. And then there's obviously variations on that, but the first real comparison that we would have would be this actual column here that has a load that is both pinned at the top and bottom, and what that theoretical carrying capacity is. So, and these factor into the formula, this K value, to tell you what the carrying capacity is of any column that you might be designing. So once again, that's what that column area is. I've already mentioned the idea of figuring out or trying to calculate the idea of the tributary area on this. And we have this idea of what kind of beam structures are needed here to support the load. And I point your attention to that idea that we just discussed about the tributary area at the end columns not needing to have as large a column. So when we get to this, we have this last column that's supported, but these outrigger columns are much thinner because they're carrying less load, less tributary load. And I hope you're motivated to do this and think through this project, because these, once again, I'm showing you this image because this is a very common kind of technique used today, especially when we're trying to float photovoltaic arrays around. And many times we don't even have enough room on the rooftop for the amount of capacity. And the attendant advantages in many climates for these kind of structures is to create a solar cooler shaded protected area around the building, which can help with energy load and cooling requirements. And I've already shown you these two. What I wanted to do now is just take a few minutes to show you some of the details, the construction details of this project. And this is kind of where I got some of the data that I was using and how I'm creating elements. So here we have on the left kind of like almost a full component assembly here. We have the top of the column system. It comes to a point here. It looks like it actually might be a rigid connection, not a pinned connection, but because it's tapering, I think it's kind of a mix between the two. We're not at that level of structural engineering to really understand that, but this shows you kind of the level of detail of quality of the exposed structural steel, the fit and finish of all of the components that are coming together. And these modules are actually going up on the building this way, and then there are hidden connectors that join these elements together. I believe this one's a mock-up just because of the way the ends of these things appear, because when we look at the one on the right here, we can see that there are bolt connections in black here for the joining of one element to the next. So there was a wealth of information about some of this componentry that you could find on the internet when I did it. I don't think it's hyperlinked. I just clicked on that just to see if it was. But here's a nice model that was made of it. And here's kind of a detail about these two levels of beam and component systems. In the project, as I lay it out, I've really removed the concept of these kind of reflective light louvers and really tried to think of it more as the placement of solar collector panels. So there's just another view of that kind of gridded system. Giving you an idea of the arrangement of the full structure from the front elevation with only one column to actually in the rear there are multiple columns. And then the idea here is actually, if you look, it looks like these columns actually terminate here. They may not actually go down through the building. They may just sit on structural steel beams of the building itself, and think that the building itself is doing a really important function, and that is stabilizing this whole structure. So the building itself has to act as the shear wall in order to stabilize and support that gridded system. So here's some other details of that kind of a system. You can see up here in the top this idea of where the numerous amount of bolting that occurs at the juncture of these components. And this last one was just how I kind of scaled it. I took a Google's map of the top view of the building. What an amazing clean footprint or ceiling roof plane that makes. And then I tried to figure out approximately by taking a scale about how big that was in order to determine those modules. So I just put this in the lecture to get us set up. I spent a lot of time trying to get all of the kind of dimensionings at least within the ballpark of where they needed to be for this, so that we were scaling things properly. And in the actual project, we'll start to get right into the details of how we're going to create these elements.